Okay. Okay, let me put back on full screen. Yeah, as I was saying, I'm going to talk about work that I've been doing over the past few years, actually. It's a series of papers that I've worked on. And the ultimate goal is to see a different form of generated gravitational waves. It was mostly focused on the CMB, but the same logic and the same models can, in principle, be used at smaller scales. And I'm gonna my eventual goal is to see what sort of observational handles we can have on high energy physics models. So inflation, why do I care about inflation? Well, because it is a very simple way to solve the problems of the old Big Bang theory, the horizon flatness problem. And most importantly, it gives us a framework to compute things. Right? So it gives us a very consistent framework of computing fluctuations in the matter power spectrum and in gravitational waves, and we're going to go out and measure things like the spectral tilt, NS, and non-Gaussians, and so on. And so far, the remarkable thing is that there's a million models of inflation out there, but the data are okay with simple single-field models of inflation in that they predict a largely Gaussian power spectrum, which is what we see, and the spectrum is close to scale invariant, but not scale invariant. Again, that's exactly what we see. The n sub s is 5 sigma away from 1, so the spectrum is not flat. So far, inflation has succeeded in giving us all the predictions, although the one prediction we have not seen yet is the presence of gravitational waves, right? And we have not, and there might be there at any scale practically, right? But as we will see, gravitational waves are a very important way to probe inflation. So again, the simple.
Sorry.
Yes.
Can people see the slides completely? I can't.
Oh really? I have it in full view mode.
Maximilian, you see the screens completely? The slides only on the left hand side there. Maximilian, how do you see them?
No, I can't see them.
Oh,
sorry, I was muted. Is there a cut on the left? Yes.
Oh, really?
Yeah.
Now we see them better.
Okay, no, not that. Oh, really? Now you see them better? Yeah. Okay. Let me see what I can do.
Okay. Now they're complete, although they are a bit blurred, but that's better.
Just a second. Let's see. So are they whole now? I mean, before I wasn't.
Okay. I mean, they're a bit blurred, but at least they show it completely.
Okay. Good. So the simplest model of inflation you can write down consists of a gravity term, m Planck squared over 2 times r. That's the usual Einstein-Hilbert gravity term. Then a kinetic term for the scalar field, right? d phi squared, and a potential. And again, the way we analyze single field inflation is by writing down the Klein-Gordon equation and neglecting the second derivative, and getting rid of the acceleration to get what's called the Slow-roll equation of motion. And Slow-roll equations can be only applied when you have the Slow-roll conditions satisfied, so epsilon and eta much smaller than 1. And in simple mechanics terms, you get the velocity and the acceleration of the field to be much smaller than unity in some normalized manner. And the good thing with simple models of inflation is, one, you know epsilon and eta, you immediately know the observables, right? NS and R are just functions of epsilon and eta. And by looking at the expressions of epsilon and eta in terms of the potential, you just see that you want the potential's derivative and second derivative to be small, right? So v double prime over v has to be much less than 1. And that sort of brings us to the problem, right? So the eta problem just comes from thinking of inflation in an EFT kind of way, right? So you write down the potential with some terms you care about, and then you have an infinite tower in principle of Planck suppressed operators. Now, once the field value is large, is of the order of the Planck scale or even more, then all the Planck suppressed operators become, Planck enhanced operators, right? They're not suppressed anymore, which means that at some point you lose predictivity of your model, right? So you can tune a potential to be flat so that epsilon is much smaller than 1, but once you take all the quantum effects into account, all the higher order terms into account, then you essentially lose the flatness of the potential, because typically higher order terms can be order 1, unless you somehow have to tune an infinite tower of terms to be very small. So essentially, large-scale models of inflation suffer from UV sensitivity. And that gave birth to a very kind of simple but very elegant solution to use a pseudoscalar field to act as an inflaton. So essentially what a pseudoscalar field is a scalar field or a quantum field that observes a shift symmetry, right? And a shift symmetry means that the Lagrangian has to be invariant under phi goes to phi plus a constant. And well, of course, once you impose the shift symmetry, it's impossible to write down any potential, but luckily, you can break the shift symmetry by instanton effects, as was done in the original paper by Katie Fries and others in 1990. And then you get a potential, and the most famous potential you get in axion inflation or in natural inflation is the cosine potential. Now, as a model builder, a very interesting thing for me.
Can I ask one thing?
Yes, yes, yes.
A question. So this looks like the similar problem of the hierarchy problem.
Yes.
So why can you solve it here with an axion, and instead in the standard model you cannot? I mean, you typically sort of supersymmetry or something like that.
Well, I mean, here I think the idea here is that here you kill all terms, right? It's not exactly the same problem. Here the problem is you have some higher order operators that you don't control. It's not like you have a difference. You just have some higher order operators that you don't control, and you want to kill all of them. And that's why the shift symmetry does. It kills every higher order term in the potential. Yeah, but the only thing
you have a scale.
Yeah, go ahead.
So typically, what you get is you get quadratic divergences that correct your potential, and this is so they're very much cutoff dependent. So it looks like the same problem as the hierarchy problem, no? I mean
Well, the standard model definitely has more than scalar fields. So yeah, I'm not. I don't know exactly why or how you would remedy that in the standard model by just imposing some sort of shift symmetry. Mm-hmm. Does not look straightforward to me at all.
I know what it is. Okay.
Yeah. Okay. So yeah. So once you impose this, the thing that simplifies our lives tremendously and makes those models very predictive as inflationary models is that the couplings to other fields also have to obey the shift symmetry, which means you can only couple an axion derivatively to other fields. And here I write the lowest order couplings to gauge fields and fermions, and you see both of them are derivative couplings. In red, you have a coupling to the axial vector current, and there's a d mu phi there. And on the left, you have a Chern-Simons coupling, phi FF dual. And although this does not look like a derivative coupling, of course, you can integrate by parts one of the F mu nus and take one of the derivatives and put it on phi. So this is a hidden derivative coupling. So both of them have very interesting phenomenology. So fermions, for example, can create some sort of lepton asymmetry through a helicity asymmetry. It's a very interesting thing. We've written papers about it, but it's not the topic of my talk. U1 gauge fields have very, very, very interesting and extensive phenomenology that is relevant for what I'm going to say. So on the left, I just wrote down the equation of motion for a U1 gauge field with this Chern-Simons coupling. Plus minus refers to the two helicity modes, left and right. And what you see here, you see that the effective frequency has a plus minus in it. And essentially, the effective frequency can become tachyonic, can become negative for certain values of the parameters and one of the two helicities. And essentially, that's what you see in the picture below. The green is one helicity and the brown is another helicity. And you see the green just skyrockets up. So what happens, again, is that one of the two helicities gets tachyonically amplified. The problem is that, or that's very interesting for preheating, for example. You can preheat the universe completely. You can transfer all the... Yes.
Can you give some more details? So the left-hand side, this is a plane wave?
This is essentially the real part of a plane wave. That's why if it was the magnitude, I read the magnitude is actually the real part. So this is just a plane wave, and blue and red is without any coupling. So conformally coupled E&M field, it just happily lives there. And the green and the brown is once I turn on the coupling, and they're the two helicity modes. So one helicity mode starts growing even during inflation and towards the end of inflation, right? The end of inflation is at t equals 0, and we see it grows by orders of magnitude more than the brown one. So there's a huge helicity asymmetry there. And during inflation, only one of them starts growing. So essentially what happens, and this is, as I said, this is very interesting for the late inflation, let's say the end of inflation. And we have shown that just by using the hypercharge field of the Shannon model, you can produce large-scale magnetic fields at the end of inflation through that mechanism. But during inflation, it's not very interesting, because once you produce the abelian gauge fields, then once you produce a lot of them, they back react on the inflaton. The inflaton slows down, which means phi dot, this phi dot parameter becomes smaller. So the fields are not produced anymore. They're allowed to redshift. So it's very hard to sustain them during inflation, is what I'm trying to say. However, this is just for U1 fields. You can play the exact same game of having an axion in red here, right, the chi field, a gauge field, right, FF, but instead of having it being a U1 gauge field, you have it be an SU2 gauge field. And this is not, again, from a model building point of view, this is nothing crazy, right? We know SU2 gauge fields exist in nature. So it's actually a very natural thing to consider them during inflation. So the interesting thing with gauge fields is that with SU2 gauge fields is that they have a non-trivial vacuum structure, right? U1 gauge fields do not, SU2 gauge fields do. So here, you can actually put the SU2 gauge fields in a very specific configuration in which you mix space-time indices and gauge indices, right? So this specific configuration of A, I alpha going like delta I alpha, J alpha. J alpha are just the Pauli matrices, are just the generators of the SU2. And first of all, this seems to be a weird choice, but the interesting thing with this choice is that when you do a rotation in real space, you can undo it by a gauge transformation. So essentially, rotations in three-dimensional space correspond to gauge equivalent configurations of the gauge field. And it has been shown in 2011 by Malek Nejad and Sheikh Jabari that this configuration is actually stable. So during inflation, if you perturb it a bit away from it, the background system will return to it. And the final interesting ingredient that is important for inflation is that we have hidden a scalar field inside the gauge field, right? So psi of t is just a scalar field. It's a number. So in a sense, we have hidden a scalar degree of freedom inside a gauge sector. So
sorry,
yes, go ahead.
I'm confused. So the SU2 is global or is local?
Local.
So it's a Yang-Mills field.
Yes.
So what's the kinetic term for these fields?
Well, we have here the FF squared. Like
okay, that's the blue one. Okay.
Sorry. It's essentially I color coded. So the green is the gravity, red is the inflaton, and this is the gauge field and the Chern-Simons coupling.
Yeah. Okay.
Yeah, sorry.
Sorry.
So if I go and count degrees of freedom, then what I have is the SU2 sector contains 6 degrees of freedom, the gravity contains 2 degrees of freedom, well, the graviton, and the axion is 1 degree of freedom. So altogether, we have 9 degrees of freedom, which you break down into 3 scalars, 4 tensors, and 2 vectors. The vectors I'm not going to talk about anymore because they're not important. So I'm just going to focus on the orange and the brown here, the scalars and the tensors. So at the background level, what happens? So at the background level, if we just go back here, we have the chi field, right? Obviously, it has a background field. It's a scalar field, it's a condensate. And psi of t is also a background field. So here, psi and q are the same thing, 2 order 1 numbers, so they're not important. So if we write down the equation of motion for chi and q, we can again do a slow roll analysis. And if you just look at the chi equation of motion, you see that on the left-hand side, you get extra friction terms. So essentially, the presence of the SU2 field creates an extra friction on the axion. This means that actually the axion can slow roll on a steep potential. This also has implications for swampland ideas, right? Because we can actually have slow roll inflation in as steep a potential as we want, practically. And that's still fine. In a sense, it's a generalization of warm inflation. So you can, I didn't write them down, but it's straightforward to write down the slow roll equations of motion for chi and q, and numerically they agree very well with the full numerics, as shown by Peter Atzett and Mark Wyman in 2012, from which those pictures are. So now that we know what happened with the background, let's actually go and see the 4 tensors and the 3 scalars, right? So let's look at the 4 tensors. So what are the 4 tensors? So everyone, we all know that there's 2 tensor modes in gravity, right? There's the gravitons, they're massless spin-2 fields, so they have 2 degrees of freedom. In this case, the gauge sector also has a tensor mode in it. And we can write the gauge field as the background value times a tensor mode. And if we write down the equations of motion of the two, so in blue here, you have the good old graviton equation of motion, right? It's actually box squared times graviton equals 0. And we parameterize them as 1 new scalar and 1 new vector. So again, I'm not going to talk about the vectors, but I am going to talk about the scalars. But let's start with the tensor mode. So as I said, the hope is that we suppress tensors. So this is the new equation of motion for the tensor modes. This is the mass, m squared over tau squared. And these are the results. On the right, we have the evolution of the gauge field tensor modes. And on the left, we have the evolution of the gravitational wave tensor modes. So actually, we see quite the opposite of what we were hoping. As we increase the Higgs mass from 2.5 to 5, we see that the amplification in the tensor modes and in the gravitational waves is larger. So we did the exact opposite. What happens, this is counterintuitive, but what happens is that this Higgs mass makes the axion roll a bit faster, and the faster the axion rolls, the higher the exponential amplification. So we actually did the exact opposite of what we were hoping. Is that a game over? Maybe no. Because if you look at the scalar modes, right, the density fluctuations, they show the exact same behavior. Larger Higgs masses tend to amplify scalar fluctuations more. So now the question, now it becomes a numbers game. Can the scalar modes be more amplified than the tensor modes to bring R down? And actually, the answer is yes. So these colored lines are a very detailed parameter scan, right? So different colors correspond to keeping various parameters fixed and varying other parameters. And we see that we nicely flow through the Planck regime. So remember, the original Chromo-Natural was up here. So what happens is we start from up here and we go all the way down there, passing through the Higgs regime. Now, the interesting thing is that because the gravitational waves are not just vacuum gravitational waves, they are not equal to h squared, right? So usually what happens is that gravitational waves are exactly equal to the Hubble scale, well, modulo 4 pi. So you need high scale inflation to produce gravitational waves. Here, to get gravitational waves of 10 to the minus 3, for example, instead of requiring the Hubble scale to be 10 to the minus 6, we only want it to be 10 to the minus 8. So essentially, we produce gravitational waves at a lower energy scale than would have naively been required. Okay, now, so okay, let's say I measure R. Do I know that it is of one nature or the other? Well, yes, I can know. This is the tensor tilt, so the spectral tilt of the tensors, of the gravitational waves. The black line here shows us the consistency relation for single field inflation. So in single field inflation, both R and the tensor tilt are controlled by epsilon, so they're connected by a trivial formula. One is minus the other, and this is exactly this line. On the other hand, we see that for the gravitational waves we produce, the tensor tilt can be either red or blue, and it's, in a sense, it's highly unlikely that it will be exactly on this black line. It can be scale invariant, but it doesn't have to be. So we get a much more rich phenomenology for gravitational waves. Now, I started motivating this by having the axion field. Now the question comes, do I need the axion, or are gauge fields on their own enough to give me what I want? It turns out we can actually integrate out the axion at some specific limit, and that generates a nonlinear term in the SU2 gauge field. Right, so we get a gravity term, a gauge field, and instead of the Chern-Simons coupling, we get some nonlinear term of the gauge field tensor. You can show that one corresponds to the other in some specific parameter regime. Long story short, in 2013, Marco Peloso and his team computed the gauge-inflation fluctuations, and again, they are way too big. So R is, again, way too big for any reasonable parameter. So gauge-inflation is dead. Then we ask the exact same question. What if we Higgs the SU2 gauge sector again? And it turns out that once more, the Higgs rescues us. The exact same phenomenology happens. Tensors get more amplified. Scalars get even more amplified, so you can push R down. The very interesting thing is that here, the shape of the tensor tilt is completely different, right? So you see it's predominantly blue. So as a model builder, if I want to talk to an observationalist, no, not to an observer, usually we have two things with inflation. We have a smoking gun and a holy grail. So the smoking gun for inflation versus its alternatives is that inflation gives you almost scale invariant gravitational waves, whereas other alternatives like string cosmology can give you a blue spectral tilt. And the holy grail is, of course, that the tensor scalar ratio is one-to-one connected through the Hubble scale. So let's see how this holds up in the light of these new models. So I have here a famous paper by Brandenberger et al. Claiming, in a sense, that if you see a blue tensor tilt, then this is a smoking gun for string cosmology. But in our gauge field models, we get NT bigger than 0 without asking for it. So this is the important thing. We did not go out trying to mimic string gas cosmology. It just happened. And furthermore, you see here on the same plot, chromo-natural inflation and gauge-inflation. And you see that one has the tendency to be red, the other has a tendency to be blue. So yeah, yes, they overlap in a small regime, but more or less they are distinctive. So even though gauge-inflation was, in a sense, born by integrating out the axion field from chromo-natural inflation, they do give distinguishable predictions. So we definitely need better ballistics in the sense that R as a number is not enough to distinguish between inflationary models. Right? We need much more from the experimentalists than just a number. And of course, the holy grail of inflation, again, is turned upside down because seeing gravitational waves does not give us the scale of inflation, because here I have given you a plot of the blue line is the naive expectation from single field argument, and red is what we get with gauge field models. And you see we can suppress the energy scale of inflation by at least 2 orders of magnitude with respect to the naive prediction. If we see gravitational waves, it does not immediately tell us when inflation happened. We need more information. Right. So as a pre-summary, as a halfway summary of what I said so far, we have this new class of models that are, to be honest, very hard to compute because the fluctuation analysis is a complete mess, but are very easy to write down. Right. So you just write down a simple axion, a gauge field, an SU2, and that's it. That's all you need to write down, and maybe Higgsed. They can be made consistent with Planck, right? Which means they are viable inflationary models, and they do not suffer from the eta problem and UV sensitivity. So they're even theoretically motivated inflationary models, and they give predictions for inflation that are very distinct in the sense that they give a spectrum of gravitational waves that is different from single field inflation and can be detectable in the near future. And something that I did not discuss, but there's a lot of literature on it, because the gravitational waves we see are not vacuum gravitational waves, they are highly non-Gaussian. So in addition to the spectral tilt, spectral tensor non-Gaussianity is also a smoking gun for these types of models. Now, one problem that these models have is that you can see most of the parameter range lies outside the Planck regime, and only a tiny bit lies within it. Right? We can tune them to give us the Planck data, but they don't naturally go to the Planck data. So there is one way around it that was proposed in 2016, which is to take all the good things that these models have to offer us, which is a large gravitational wave production and tensor non-Gaussianities and so on, but add them as a spectator sector on top of an inflationary sector. So now this starts becoming much uglier than it was before. But again, in view of string axiverse claims, right, the fact that you will have axions and highly likely they will be coupled to gauge fields and they will be active during inflation, there's no way not to consider them, right? They do not have to be the axion, but they will be around. They do not have to be the inflaton, but they will be around when the inflaton is active. So the requirements for what I'm about to discuss in the next 5 minutes or so is that we have an inflationary sector in green, which produces scalar fluctuations. All I wanted to do is to give me n sub s 0.966, and then I forget about it. I have the axion, which is subdominant, so it has a tiny fraction of the energy density of the universe. And I have the blue sector, which is the SQ2 sector that will give me the gravitational waves. The background evolution is exactly the same as before, right? With the minor tweak that the Hubble scale is not generated by the energy density of the axion, but in a sense, it is a free parameter, right? So this green term gives me the Hubble scale, and I plug it into the equation of motion for the axion and gauge field. The good thing is that the same amplification of tensor modes, the same exponential amplification of tensor modes is active here without problems on the scalar sector. Right? Now, this opens up a way to very quickly and easily probe a lot of potentials for the axion field without having to do the calculation of the scalar fields and exclude huge chunks of parameter space at the same time. So here we wrote down 3 potential types, right? A potential type that is monotonic during inflation, a potential that has 1 inflection point, just like the original natural inflation potential, and most importantly, or most famously, the axion monodromy model. So a potential that has a sinusoidal modulation on top of a monotonic function. So the reason why we went into these models is A, simple phenomenology, right? So what sort of potentials have been written down for axions? And secondly, because the gravitational waves are controlled by the derivative of the potential, right? So the gravitational wave spectrum has this exponential amplification, and it is depending on u prime. U prime is the derivative of the potential with respect to the field. So let's look at each of the types specifically. So for type 1 potentials, where the u potential is just a monotonic function, we can get either linear red or scalar invariant spectra. Right. So for a potential that goes like chi to the 1/2, you get a blue spectrum. For a potential that goes like chi squared, you get a red spectrum. For a potential that is linear, you get a scalar invariant spectrum. Right. So this can lead to detectable gravitational waves at the CMB, or in the case of this orange line, it might be invisible at the CMB, but it might peak towards the end of inflation, making it detectable for things like Lisa and LIGO, again, depending on parameter numbers, right? So this is, in a sense, we can start putting in interferometers to probe inflation in these weird models with strongly blue tilted spectral tilts for gravitational waves. Now, for the second family of models for single inflection point potentials, so here the important thing is that u prime, the derivative of u prime, has a maximum. So generically, these models will give us a peak in the gravitational wave power spectrum, right? So the gravitational wave power spectrum will be a peak. It will be as sharply peaked or as shallowly peaked as we want based on parameters. And again, the motivation from that, we went to a paper by Kobayashi et al. In 2016, where they wrote down some explicit constructions for string potentials. And we saw that they had this general feature. They had this general feature of being something like a sinusoidal function, right, with 1 inflection point in the region of validity of the theory. So we modeled them by a trivial generalization of the cosine potential, and this was enough for our needs. And finally, and most interestingly, in my opinion, is when we have axion monodromy potentials. So in these potentials, we have some polynomial term, let's say a linear term, and on top of it, we have a cosine modulation. So this is the hardest to analyze analytically, because you have to break down the background motion in the constant and the modulation. And well, after a few pages of algebra, you can write down the power spectrum for the gravitational wave, which has the exponential amplification that we saw before. And on top of it, it has a sinusoidal modulation. So this sinusoidal modulation of the gravitational wave, we can go out and measure. Right? So here, we did actually some predictions for LiteBIRD. So LiteBIRD is the Japanese mission that has been approved and will be launched in the next decade, I'm sorry, with aim to A, go down in R, and B, try to measure things like tensor non-Gaussianity and tensor spectral tilt. So the 3 panels correspond to different amount of modulation of gravitational waves, and the shaded regions correspond to different assumptions on what we can do with the detector. So the dark gray assumes perfect delensing and very good control of the mission systematics. So we see that in the best case scenario, and with a very large modulation of the gravitational waves, we can actually distinguish our model, which is the simple axion monodromy model, from the baseline, which is just a non-oscillating gravitational wave spectrum. So in a sense, with LiteBIRD, we will be able to start probing axion monodromy potentials through gravitational waves. So doing a string tomography of gravitational waves. So again, as an experimental roadmap for future CMB missions, we don't just go out and measure R. We measure R, assuming we find it. Then we have to measure if it's red or blue or scale invariant. We have to measure if it has parity violating modes. So if one helicity of gravitational waves is exponentially more enhanced than the other. Then we measure tensor non-Gaussianity. If all of those are negative, then we have discovered quantum gravity. We have discovered vacuum fluctuations of the graviton that are exponentially stretched by inflation. If not, we have actually discovered seeded or gravitational waves that are generated by some form of quadrupolar Tij, right, of a stress energy tensor of some fluid with a quadrupolar anisotropy. In this case, in the models that I discussed, we discussed some axions coupled to gauge fields that produce these sort of tachyonically amplified gravitational waves. So in a sense, if we discover this sort of signal in the CMB, we are starting to do string phenomenology on an unprecedented energy scale. So if I have 5 minutes, I can give you a bonus, which again, we did not go asking for it, but it's free. It's there, and we can actually take advantage of it.
Please go ahead.
Okay, thanks. Which is the gravitational anomaly of the standard model. So once we get helical gravitational waves, right, the standard model will produce a B minus L asymmetry, right? So this R dual, or this gravitational Chern-Simons type term, goes into the gravitational anomaly of the standard model and creates B minus L current. And that's exactly the type of thing we get from these models, right? We get a large amount of chirality in gravitational waves. So the number density of B minus L violation goes like the energy scale of inflation times this asymmetry in the polarization of the power of gravitational waves. So the question now comes, what sort of numbers do we need and what can we learn from them? And are they enough to give us the B minus L we actually see on the sky? And the fact that we're made of baryons, not anti-baryons. So the baryon asymmetry, again, divided by the observed value of 10 to the minus 10, goes like the Hubble scale at the end of inflation, times the reheat temperature, times the asymmetry in the gravitational wave power spectrum. And we see that for high scale inflation, this is actually viable, right? 10 to the minus 10 is here. So we can actually, through this simple mechanism, if we get enough polarization of gravitational waves, we can actually generate the asymmetry that we need. Although we need high Hubble scale and high reheat temperatures. Now the question arises: what do reheat temperatures do for you? So in general, when you have a high reheat temperature, everything is in equilibrium, and you might be worried that things will be washed out, and indeed they might be. So that's what we essentially, that was the naive picture that was put forth by papers up to that point on gravitational leptogenesis. And we wanted to do a bigger scrutiny of those models in view of washout processes. So then we have to ask, okay, usually leptogenesis models require some form of heavy neutrino to augment the standard model neutrino and give the mass, like a type 1 seesaw mechanism, for example. And then we have to ask ourselves, what are the neutrinos? Right? So there are two, of course, two and only two options. The neutrinos can be Dirac or Majorana. Right? If the neutrinos are Dirac particles, then no let Neptune number arises, because this gravitational anomaly will create essentially no net helicity of neutrinos, because it will create a left-handed neutrino and a right-handed anti-neutrino. However, there's an effective lepton number that is created because the right-handed neutrinos are sequestered from the Standard Model. So they will be created, but they do not talk to the Standard Model. They are somewhere out there as a tiny fraction of dark matter, and we don't care about them. So effectively, the Standard Model will have an effective axial Standard Model lepton number through this process. And there, no washout is needed. Now, if the neutrinos are Majorana particles, then by introducing these heavy right-handed neutrinos to do the seesaw mechanism, we will get these types of washout processes in which you get a lepton interacting with a Higgs and a heavy neutrino and coming out an anti-lepton, right? So essentially, Majorana neutrinos can flip the helicity or the lepton number of a particle. And this immediately leads to a suppression of the helicity asymmetry that's produced, right? There's a partial washout of what you produce. Now, again, once you start thinking about those things, you say, okay, I want my neutrinos to be as heavy as possible, right? To have the minimum washout possible. Although that is not actually needed. Let's assume you have a neutrino mass that is much lower than the Hubble scale. In this case, the lepton asymmetry carried by the left chiral leptons is washed out completely. Now, the lepton asymmetry carried by the right-handed leptons is then redistributed in the rest of the Standard Model, where when the Yukawa interaction comes into equilibrium. This means that not only do you get a lepton asymmetry in the Standard Model, but you get a lepton asymmetry of the opposite sign than you would get if the neutrinos were heavy. And here we get on the horizontal axis the mass of the heavy Majorana neutrinos, and the color corresponds to whether your lepton number has the same sign or a different sign from the original gravitational wave helicity that produced this lepton number. So you see that if you measure the helicity in the gravitational waves and whether it agrees or disagrees with the lepton number we have today, you can infer if the Majorana neutrinos were heavy or light. So this creates, in a sense, a very complicated interaction of observations, right? So we measure gravitational wave helicity either through CMB or interferometers. We check if this is enough to produce the baryon asymmetry through gravitational leptogenesis, and by running the numbers, we can infer both the neutrino nature and the neutrino mass in terms of Majorana neutrinos. And of course, by studying the gravitational wave spectrum, we can learn about the axion. So in a sense, we can put together multiple pieces of information and multiple pieces of physical processes to learn at the same time, assuming, of course, we detect the gravitational waves, to learn about the axion potential and Standard Model processes like the neutrino nature and neutrino mass, the heavy right-hand neutrino mass. So that was all that I had to say for today. And if you have any more questions, I'm very happy to discuss.
Thanks for your talk. I will now open for question and stop the recording. Thank you very much for your talk.
Okay, thanks.